Okay, good morning, everybody. Welcome. As most of you know, this is a special edition of the workshop celebrating 20 years of the meeting. Many collaborations out here, and hopefully many will come. I wish you a pleasant and fruitful week. And it's a special pleasure to introduce Victor Ginsburg from Santa Cruz. I think his first participation was in 2007, right? Yeah, sure. Yeah, I think not the first one, but the second one, yes. So 18 years ago. And he would talk about, barcode growth and Ruby dynamics.
Thank you. Yeah, it's been, give or take, 20 years, and a lot of things have happened in these 20 years. Some of them are, a lot of things have changed. Some of them are not to the better, but there was one constant and reliable thing, and this is this workshop. It's always been great, and it's a pleasure again to be here at IMPA, and in the city is as beautiful as ever. So what I'm going to talk about is indeed the barcode growth and rep dynamics, and the talk will be mainly based on my joint work with Erman Cinelli and Bashak Gorel and Marco Mazzucchelli and some other people, which I will mention along the way. And it's based on it's an installment in a relatively recent project, which is about the question how much dynamics can we see through Morse or Floer theory of a dynamical system. So basically the idea is, let's start with a Hamiltonian dynamical system. For instance, it can be a Hamiltonian diffeomorphism, or a geodesic flow, or more generally a rep flow. So here I'm going to focus on rep flows, but you can think of a geodesic flow if you prefer. It makes very little difference. In fact, geodesic flows are already as interesting, as complex as general Hamiltonian dynamical systems. And it has dynamics features. For instance, something traditionally investigated by symplectic topological methods would be periodic orbits or chords. But here we are interested mainly, not exclusively, but mainly in dynamics features that go beyond, for at least formally speaking, go somewhat beyond periodic orbits. For instance, topological entropy. And then, so an exclusive feature of Hamiltonian dynamical systems, in contrast with more general dynamics, is that you can study them via Morse theory. So you put here Morse or Floer theory, and the minimax principle. So, and via the minimax principle or whatever like variant of Morse theory you want to use, you can associate what is nowadays called a persistence module to a Hamiltonian dynamical system. And my question is, how much information about dynamics can you get from this persistence module? So how do you go here? For instance, can you see the topological entropy of a system via this arrow? So that's the question I want to address. And of course, it's a very classical matter in some sense. It's been studied for a long time. But I want to look at it maybe on a finer scale. So when we have homological growth, it's well known that one can get that it's captured by Morse-Floer theory, and one can get topological entropy or a lot of dynamics just from this arrow. But what happens if you don't have topological growth? What happens if you say you look at the geodesic flow of a metric on the sphere or the torus? It can have incredibly complex dynamics. It can be ergodic. It can have positive topological entropy, you name it. But a priori, it's absolutely unclear how to make this transition. And this is what the project is about. So now, that said, are there any questions about what we are trying to do here? Are we all good? All right. Then let me describe the formal setting here. So M will be the boundary of a Liouville domain So it has a symplectic form omega equal to d alpha. And sometimes I will need to, sometimes it is useful to have the symplectic homology of that Liouville domain graded, and then I'm going to assume that the first Chern class of the tangent bundle is 0, but mainly it doesn't matter. Then on the boundary, I have the Reb vector field X. It's characterized by the condition that the contact form on X is equal to 0, and the contraction of X and alpha is, the contact form is 1 and the contraction is 0. The examples to think about, or to keep in mind, the examples I'm mainly interested in are, first of all, a star-shaped domain in R2n or a star-shaped domain in the cotangent bundle to some closed Riemannian, to some closed manifold. So this one would be fiber-wise, star-shaped. For instance, this would be the unit disk bundle of a Riemannian metric. Both examples are very classical nature. So then when one can associate to W, the filtered symplectic homology. SHT of W or SHT of alpha. Here T is a real number, non-negative. And there are several ways to, okay. So this is a family of vector spaces over some fixed field F, which might be the set of rational numbers or Z2. And it's useful to keep it open here, the field of your choice, parameterized by real numbers T. In fact, let me just say it's T in R, but the vector space, the homology for negative T's is 0. One possible, there are many definitions, and I'm going to very briefly go through some of them, but probably the simplest one is this. Let's form the symplectic completion of W, which is the union of W along the boundary with the product of the boundary with the interval 1 infinity, denoting here the coordinate by R, and the symplectic form is omega on W and dr alpha on the con part. So this looks like something like this. Here is, actually I'll sketch it elsewhere. Let's put it here. So this is W. This is the con. This is M. This is M cross 1 infinity. So omega dr alpha. So this is what the completion looks like. Now let's consider a Hamiltonian on this completion of the form. It's identically 1. So, sorry, identically 0 on the W part. Then it is convex as a function of R, and eventually it switches to a linear function AR plus B, where A is outside the spectrum, the action or period spectrum of the Reb flow. Let's call such Hamiltonians H. So one can define the symplectic homology of W as the limit over all such Hamiltonians as they grow steeper and steeper. Of the Floer homology, so this is the direct limit of the Floer homology up to the energy level T. Assuming non-degeneracy of the flow, Okay. But one can actually do a little bit better than that. And the problem with this definition is that it involves a direct limit. And limits are always bad. You know, like when you teach calculus, it's always a big problem, like the limit. It's one of the most difficult notions. And I definitely don't like them. So in fact, no limit is necessary here. And the symplectic homology up to the level A is simply equal to the Floer homology of the Hamiltonian H, where the slope of H is equal to A. So I don't need to pass to any limit. I can take any Hamiltonian with the slope A. So, and this is much more convenient. So alternatively, in the non-degenerate case, the symplectic homology can be thought of as the homology of a complex generated by well, first of all, I'm going to take the critical points of a Morse function on W, which is gently increasing near the boundary and constant on the boundary. So the graph of this function looks like it wiggles here, and then it increases to some constant near the boundary. So, and then for each periodic orbit of the rep flow, I'm going to associate two generators, x hat and x check. The x hat will have the degree equal to the Conley-Zender degree of x plus 1, and the x check will have the degree equal to the Conley-Zender. And then there is some differential.
Then you're assuming that the Briggs flow is non-degenerate.
Yes, this is in the non-degenerate case. And strictly speaking, yeah, it's in the, but in any event, this is how intuitively we should think of it. And there is, of course, a differential one has to define, but it's always immaterial what it is, because nobody can actually compute it in a non-trivial case anyway. So this is the symplectic homology. And now I'm going to say a few words about persistence modules. So this is a formalization, axiomatization of the notion of symplectic homology or sub-level homology of a function. So we have a family of vector spaces over a fixed field, parameterized by a real number t, together with structure map from a space Vs to space Vt, where S is less than T, having all obvious functorial properties. And in addition, I will require the spaces to meet the following requirement, to meet the following conditions. First of all, it's 0 when T is small. And for our purposes, I'm going to set this threshold to be 0. 0.
You write equal 0. Or you just didn't write equal 0.
So I'm saying this is like still small.
Right. No, you said that is equal to 0.
Okay, okay, let's, yeah. Secondly, I don't require the spaces to be finite dimensional, but I want the rank of the sorry. Start again. I want to say this differently. In addition to the structure, I want to fix a subset S of real numbers called the spectrum, such that pi st is an isomorphism when S and T are in the same connected component of the complement to the spectrum. And for this to make sense, I want the spectrum to be, say, nowhere dense and closed. So that the complement to it is a union of intervals, and whenever S and T are in the same interval, then pi st is an isomorphism. So this is a set of points where the space Vt can possibly change, but it does not have to. So now I'm imposing the following conditions. The first one is that the space is 0 when T is below a certain threshold, and I will assume that this threshold is 0 for our purposes. Then I'm going, yeah.
You want to say that Vt equals 0.
Yeah. Thank you. I was kind of wondering what it is you guys are unhappy about. Okay. Well, you know, there should be these little things challenging the audience to keep your attention from wandering. So, the next one is that the rank of pi st is finite when S is strictly less than T. So the point is that, like, even when S and T are not in the same interval, the transition from S to T has a finite rank. I do not require the spaces in themselves to be finite dimensional. So this condition is referred to as Q-tame. And finally, I want it to be left semi-continuous.
So the rank is finite dimensional, but when pi-st is an isomorphism, that implies that Vs and Vt are finite dimensional.
Yes, this is why I want S to be strictly less than T.
S and T are the same connected component.
So then it is an, yes. But so if you are in the complement to the spectrum, then the spaces are finite dimensional. They can become infinite dimensional only at the spectrum points. And this is perfectly allowed. In fact, by the same token, we can just have this whole thing defined outside the spectrum, required finite dimensional, and then extend it to the spectrum by left continuity.
So, but in that finite dimensionality rank condition, it means that S or T can be in the spectrum.
Yes, definitely.
That's when,
So when you approach a spectrum point from the left, you are going to get always finite rank. Yes. So a good example here, and the example that sort of sits behind this all, well, first of all, to connect this with our discussion is that the SH of W, I'm suppressing T here because it's a variable, is a persistence module. I'm not imposing any non-degeneracy conditions. So the symplectic homology is a persistence module. If C1 is equal to 0, then moreover, it is a graded persistence module. That's the obvious definition. But the mother of all examples is, of course, this. Let's take a function on some nice on a manifold P to R. And I want it to be proper and bounded from below. And I'm going to take Vt to be the homology of the sublevel f less than t. And now I want this function to be sufficiently smooth so that Sart's lemma applies. I don't care whether it's Morse or not, but I want it to be sufficiently smooth, and this is a persistence module. So every persistence module under these conditions can be decomposed. All right, so there are two sides to persistence modules. One of them is purely algebraic, but there is also some geometry involved to them, which I'm going to suppress in this talk entirely. But these are purely algebraic objects. One can take direct sums of them, quotients, there are maps, blah, blah, blah. So in particular, here is a fact which has been proved by many people. Ultimately, this is the Jordan normal form theorem, that every persistence module can be decomposed as a sum of the so-called interval modules, which I'm going to describe right now. But essentially, these are simple objects. These are prime numbers or simple groups in the category of persistence modules. And these are the following guys. Let's take A and B. And let's take the module which is identically equal to our ground field F in the range from A to B and 0 otherwise. With the structure maps, what you think they are, 0 from here to there, 0 from here to there, and isomorphism here. Or we can allow the interval to be infinite. And the module is F from A on and 0 before A. Observe that these guys are in one-to-one correspondence with the total homology involved in this space. So such intervals are called bars. The intervals entering into the decomposition is unique up to rearranging the bars in the direct sum. And the infinite bars are in one-to-one correspondence with the homology, with the total homology involved here. For instance, in the example here, the infinite bars correspond to the total homology of the manifold P. And for symplectic homology, we get the total symplectic homology of this thing. And these guys are here, the infinite bars are in one-to-one correspondence with spectral invariance. I could have done the same thing for equivariant symplectic homology. So these infinite bars are in one-to-one correspondence with spectral invariance. And one remark is that the symplectic homology persistence module is an invariant of the interior of the Liouville domain. I don't know who to attribute this fact. Chilibach, Floer, Hofer, Jean Good, I don't know, it's been rediscovered, reproved many, many times. And actually, one reason for this is that there are at least two very different definitions of symplectic homology in circulation carrying different information. So for some of them, this is tautological. Are there any questions? Now I want to associate a numerical invariant to a persistence module. So let's fix, again, I have a persistence module, Vt, or Vs. Let's look at the decomposition of that persistence module into elementary persistence module, and the barcode function B epsilon of S is the number of bars of length greater than epsilon beginning below S. It's not hard to show that under the conditions here, this is a finite number. Another relevant invariant, which I'm not going to use here, but I want to bring to your attention, is simply the dimension of the persistence module. I use a subscript. So let's stick to the subscript now. At the point S. So that's another useful invariant. The two are related, but not too tightly. So it turns out that the barcode growth function, or barcode function, is related to the underlying geometry when your persistence module comes from some source, geometrical source. It's been discovered by several groups of people pretty much independently that totally beyond dynamics in various situations, this function reflects, sometimes reflects, geometrical feature of the underlying things. Let me sketch what the barcode looks like when W is an irrational ellipsoid. The x-axis here is the action or period. The vertical axis is the index. In this case, the Kondo-Zehnder index is defined. And so I have a graded persistence module. And it looks like this. I'm going to mark the action or period spectrum here. And then I have a bar starting at level n, ending, at level n plus 1. Then the next bar will begin at n plus 2 and at level n plus 3, etc. And through every point, I will have exactly 1 bar. And this is about like one of the very few examples where one can explicitly calculate the barcode, the persistence, the symplectic homology barcode. And the reason is, of course, that the differential, well, the differential is not 0, but the differential is very simple. There is not much room here for anything interesting to happen. In particular, in this case, the dimension is equal to 1. So now I'm ready to.
Can you explain a little bit how do those bars appear
So,
international website? In terms of,
so
you have orbits.
I started kind of erasing. This is non-equivariant symplectic homology, and you are probably thinking about the equivariant. So the total homology is 0 because because it's displaceable.
Bars go between those two.
Yeah,
These for each other.
Yeah, there are two generators on each orbit. The low index one is the end, the high index one is the beginning, and then it repeats itself. And there is no other way it can be. So it just has to be this way.
The target of your function is?
The target of, so this function, it's not really a function. So this is a graded persistence module. So to keep track of the grading, I introduced this extra axis. So it's not really a function, if you wish. So now, what does it have to do with topological entropy and dynamics? Definition. Let's put it here. The barcode entropy h bar sub epsilon of W or alpha, it is actually independent of the filling, is equal to the limit, the upper limit, as s goes to infinity, the log of b epsilon of s divided by s. And this is an increasing function in epsilon, and h bar of W is simply the limit as epsilon goes to 0 of h bar epsilon of W. I should, strictly speaking, put the plus here, meaning that the log of 0 is 0. So when you stare at this definition, it resembles the definition of topological entropy word for word, and there is absolutely no reason to think that it's meaningful. It just doesn't have to make sense. But however it does. By the way, a disclaimer. Okay, the disclaimer will follow shortly. So here are the results. Theorem A. And this is Fender, Lee, and Son. The barcode entropy is less than or equal to the topological entropy of the rep flow. Phi is here the rep flow. Well, this is already something, but it could be totally trivial if h bar were always 0. However, even at this level, there are some interesting consequences. For instance, that b epsilon grows, and here, of course, epsilon, I did not say it anywhere, but epsilon is positive, including infinity. So that the barcode function grows at most exponentially, whereas the number of periodic orbits can grow arbitrarily fast. The number of closed geodesics can grow arbitrarily fast. So, theorem. But still, it would be good to know that it's non-zero, right? So let's say K is a hyperbolic set of the rep flow. Theorem B. And this is Cinelli, myself, and Bashak, and Marco Mazzucchelli. Then the barcode entropy is greater than or equal to the topological entropy of the rep flow restricted to the hyperbolic set. So once you have some hyperbolicity somewhere, this thing is non-zero. Theorem C. If dimension of M is equal to 3, then the barcode entropy is equal to the topological entropy. This is a virtually immediate consequence of the theorems A and B, and the fact that in low dimensions, all of topological entropy comes from hyperbolic set, and this is like Lima Sarig and Liang Yang, and ultimately Katok.
When you say a hyperbolic set, it doesn't have to be necessarily a Hartree. It can be, for instance, a period one, an hyperbolic period one.
Yes, it could be. But of course, then this would be zero, and yeah. Yes. This is true for any hyperbolic set. So basically, the point here that in lower dimensions, all entropy comes from horseshoes. So I don't have time for the proofs or anything like that. There are two things I want to say before I finish. I have something like 10 minutes. First of all, as a consequence, we obtain some classical results. I'm listening. Yeah?
Yeah, so theorem C says because in dimension 3 you can approximate the entropy by the entropy restricted to a hyperbolic set.
Yes, the soup over, so the soup over all k h top of k is equal to h top of phi. This is what goes in there. So, classical result. It's well known concept that the growth of B infinity, or the exponential growth of B infinity, implies or relates to topological entropy. This starts with Dinaburg in the early 70s, who looked at the fundamental group growth. Then, of course, speaking here, I should mention Manet, then Gabriel Paternon. In the more modern version, it's Maccarini and Schlenk who extended these results to rep flows on cotangent bundles, then Alves and Maives in various combinations, and Babandal, and many people. So whenever you have a homological growth, you are getting topological entropy. The second one is that there is a relative version. Namely, rather than looking at periodic orbits here, one can look at Legendrian chords. Connecting to Legendrian submanifolds and use the rough Floer homology, and this is Rafael Fernandez. Both theorems A and B and C. Then there is a Hamiltonian version where instead of looking at the rep flow, one can look at the Floer homology of a Hamiltonian diffeomorphism and its behavior under iterations. And in that context, so in the Hamiltonian version, it can happen that the barcode entropy is strictly smaller than the topological entropy. This is Ermancinelli. I don't know, I'm not aware of any examples in the rep context, but nonetheless, I don't expect this equality to hold in higher dimensions. I don't have absolutely no time to talk about proofs, but I want to spend the remaining 5 minutes looking at the other extreme of the whole situation. So here, this is a picture of what happens when you have complicated dynamics. Now I want to look at trivial dynamics. Are there any questions? Because I'm going, yeah.
So is there any assumption of W for those results? Like, it's very cool.
No. Nothing comes to mind.
Or maybe any condition on the synthetic homology?
No. No. I mean, it has to be defined, that's all. But I don't even need C1 to be 0.
It could vanish.
Aha. Say it again. So here is the gist of the whole thing. Let's take a symplectic manifold. Let's take any flow and multiply it by rotation of the circle, or irrational translation of the torus. This destroys all periodic orbits, but does not change topological entropy. Now you want to do something in the symplectic, in the Hamiltonian category. So you use Zender's torus instead, which forces the underlying manifold to be irrational. And hence you cannot prequantize it, and hence it's not known in the rep case. All right, so I want to look at toric domains. So W is, I don't have time, so I'm going to skip definitions here. W is a toric domain in R2N. The point here that this is a completely integrable system with very simple singularities, with toric singularities. So a theorem of Barut and myself, the barcode growth function grows at least polynomially with the exponent equal to the half of dimension, assuming that W is convex or concave or real analytic.
You said at least, and you wrote less than or
Oh,
equal.
sorry, at most. At most. So as Michael pointed out this last week, this is obvious. You just need to take a suitable perturbation and look at the number of generators. And you get this upper bound on the number of generators. So the proof is just count the number of generators. I would expect a similar upper bound, at least sub-exponential upper bound, to hold for all integrable systems with some singularity control. There is an example of Taimanov and Balsinov and Taimanov of a geodesic, integrable geodesic flow with positive entropy, but here, there, all the entropy is packed into singularities of first integrals. There is, however, an interesting consequence of this, namely the corollary. The growth rate of B epsilon is an invariant of the interior of the domain. For instance, the topological entropy in dimension 3 is invariant of the interior of the domain. Or the barcode entropy, or the slow barcode entropy, where I replace S below by the log of S, where I look at the exponent in the growth rate. Now, this corollary extends for domains with non-smooth boundary, literally as stated here. So even when the boundary of W is not smooth. One has to be a little bit careful here, because the persistence module, the symplectic homology of persistence, the symplectic homology persistence module is not really defined when the boundary is not smooth. At least it won't satisfy all these conditions we imposed here. Remember, in the example of a function on a manifold, we needed some smoothness. However, the barcode growth function extends to the non-smooth case essentially by continuity. There are kind of by passing to the limit, fixing S and approximating your domains by the domains with smooth boundary. So there are some ambiguity of how to do it, and they are not perfect, but they will all result into the same growth rate. So as a consequence, the growth rate is an invariant of the interior. And so, for instance, if you take a generic domain in R4, it will have a positive entropy and will never be symplectomorphic, exact symplectomorphic to an integrable domain. Yet, I'm unclear on how much dynamics is visible by the interior. So, yes? These constants A and B are actually independent of epsilon. But they're not universal. They, of course, depend on the domain W because you can scale the whole thing. And when actually they can be, if the domain is not convex or concave, they can be quite large. When the domain has a smooth but not real analytic boundary, I actually don't quite know what happens when you when there are too many extrema. There is this question which is tangential to dynamics, but I still think it's interesting. How much dynamics is seen by the interior? I had a good candidate. Namely, I thought that in the case that Katoch's pseudo-rotation could provide an example of a domain where the interior sees more dynamics than symplectic homology, but last week I learned about a construction by Ababandala and Benedetti, and admire that actually the interiors are symplectomorphic too. So it's complete. I'm not aware of any example where the interior would see more than symplectic homology, unfortunately. The second interesting question I want to mention that actually nobody knows if there is any pattern to the behavior of the barcode. Even in the integrable case, let's think of the barcode as a function of S. How does it behave? Is there any pattern? Like, what's the statistics of the barcode, the distribution of length of the barcode? Even amazingly, nothing is known. Likewise, in the generic case, in the case of topological entropy, we know it grows exponentially, but is there any real pattern? What would be like the next term? What's actually going on? I think it's absolutely unknown. And finally, a disclaimer. One shouldn't think of this, of the barcode entropy as a way to calculate topological entropy. It's overall, this thing is absolutely intractable beyond trivial cases. It's just the interesting point here is connecting two a priori unconnected notions. Thank you. I'm way over time. Let me stop here.